In this video we look at the remainder and factor theorems. So the remainder and factor theorems will provide us with an easy way to factor cubic functions, quartic functions, and so on. So we'll start with the remainder theorem. Basically the remainder theorem says that if a function is divided by x minus p, that's this section right here. Let's see if we can highlight that a little bit. So if a function is divided by x minus p, giving a quotient or an answer when you do the division of q at x and a remainder of r, and this is the important part, then the remainder is equal to f at p. That might not seem like a big deal, but when we do an example, I think what will happen is you'll see. So why don't we go ahead and do an example. This first example has us finding the remainder when we divide this cubic function by x minus 2. So according to this remainder theorem, is that when we do the division by x minus 2, that's our x minus p, the remainder should equal whatever f at p is. So our remainder should equal, this is our p-value right here. Again, if you look at this, x minus p, our p-value is 2. So without actually having to do the division, we can find the remainder pretty quickly. So let's go ahead and find f at 2. Again, that just means substitute a 2 into the function everywhere we see an x. And then we can evaluate from there. So 2 cubed is 8. We can do this all in one go on a calculator, but let's just do it here in steps. Don't forget your order of operations is important. 2 squared is 4. 4 times negative 5 will give us a negative 20. And then we have a negative 2 times 2, which is a negative 4, and a positive 24. So right now I see a positive 24. I also see a negative 24 here. So it looks like our answer here is going to be 8. So that tells us that the f at 2 is equal to 8. Therefore, the remainder of the division, x minus 2, divided by that cubic function, x cubed minus 5x squared minus 2x plus 24, is equal to 8 as well. Maybe instead of an equal sign, I'll put an is in there since this is a sentence. And we can actually go ahead and do that division, and when you do that division, you'll see that you do in fact get a remainder of 8. So that's a nice quick way if you want to know what the remainder is without having to do the division. That is a huge time saver. I mean, it didn't take us very long to figure out what the remainder was without having to do the division. Now one thing I want to note here is that if the divisor is written as x plus p, so up here, remember the remainder theorem said that the divisor had to be x minus p. If the divisor is x plus p, let's just rewrite that. Let's split that plus sign into a minus sign and a negative sign, and then we can substitute negative p in there. So what I mean by that is if we were trying to divide this same function by x plus 6, then we could rewrite this as x minus negative 6, and then the remainder of that would be f at negative 6. So the sign here does matter, so just pay attention to that. It does need to be written in this form x minus p. So keep that in mind. That's what the minus sign in here. That's why we rewrote that as a minus sign. All right, so we can find the remainder pretty easily, but what's the big deal? What's the point? Why would anybody want to know the remainder? And I guess the biggest reason is to know if something is divisible, is evenly divisible. So if you know that something is evenly divisible, think about what the remainder should be. Obviously, if something is evenly divisible, the remainder should be 0. So x minus p is a factor of f at x if f at p equals 0. So if we can find a number p such that f at p equals 0, then we know that x minus p is a factor. So in the previous example, we kind of went this way. Now we're going to go this way. So we're going to try to work backwards and find a factor. So let's go through. We'll do this cubic. You already know how to factor quadratics. We're going to look now at factoring a cubic. And we can find a factor by finding an a value such that f at a equals 0. Now I want you to think a little bit here about what this looks like. I think my screen just kind of disappeared on me. There we go. So think about what that looks like for a second. What values could we substitute in? Well, if you think about it, if this thing is factorable, this polynomial is factorable, then we know that in the end we're probably going to end up with 3 factors. 3 factors because this is a third degree polynomial. We're probably going to have, an x in each of these, and then some number at the end of each of these sets of brackets. And ultimately this constant term here, this 24, is going to come by multiplying these 3 numbers together. That's how we get that number. Otherwise, every other term is going to have an x in it. Remember, the idea here is that we would multiply everything in one set of brackets by everything in the other set of brackets. Every other term is going to have an x except for the constant multiplied by the constant multiplied by the constant. So our search for an a value doesn't have to be a total random search. We're going to look at factors of 24. There's no need to look at any other numbers because one of these numbers has to work. So look at factors of 24. So I'm going to start with, let's start with 1. Let's try f at 1. So f at 1, remember, according to the remainder theorem, will give us the remainder when we divide this polynomial by x minus 1. Well, let's try it. 1 cubed minus 5 times 1 squared minus 2 times 1 plus 24. So we're going to have 24 take away 2 will be 22. 22 take away 5 plus 1 more. Doesn't matter what it is. It's clearly not equal to 0. We haven't found our factor yet. So I'm looking for another factor of 24. And sometimes you may need to consider the positive factors. You might need to consider the negative factors. I'm going to try 3 here. 3 cubed minus 5 times 3 squared minus 2 times 3 plus 24. All right, we may have to do a little bit of work here. This one's not quite as obvious. This will be 9. This will be 3 squared is 9. Times 5 is 45, minus 6, and then plus 24. So it looks like, let me just have a quick look here. I think we're okay. I'm just trying to think, oh, you know what? I was trying to do the math in my head here and realizing things were going to work out. 3 cubed is not 9. 3 cubed actually is equal to 27. That's where things weren't working out. And I think if I've done this correctly, we're going to get an answer of 0 because I've got a positive 27 here and a 24 here. That takes me to 51, and then this here is going to give me a negative 51. So that gives me 0. What that means, the fact that f at 3 equals 0, it means that x minus 3 is a factor. Therefore, x minus 3 is a factor of that cubic function. So what we can do now is we were asked to factor the whole thing. Well, let's go ahead and do some division. I may run out of room here. Let's divide this out. We'll get x cubed minus 5x squared minus 2x plus 24. So we'll do the division, and then we should get a quadratic that we can probably factor. Let me just tidy up that minus sign there. All right, so with the division, x cubed divided by x is x squared. X squared times x is x cubed. X squared times negative 3 is a negative 3x squared. Do the subtraction. So 5x minus negative 3x. So that's, we're at negative 5 plus 3. That's going to take us to negative 2x squared. Negative 2x squared divided by x will be a negative 2x. Negative 2x times x is negative 2x squared. We can bring down our minus 2x here. And then here we'll get negative 2x times negative 3 will be a positive 6x. Hopefully I can fit this in here. Negative 2x squared minus negative 2x squared is nothing. Negative 2x subtract 6x will give us a negative 8x. And there's still that 24. We'll bring that 24 down. And I think I might just try to slide this toolbar out of the way. There we go. And then we do the same thing. So negative 8x divided by x is going to be a negative 8. So we'll just add that in here. And then we'll do the expansion. 8 times x, sorry, negative 8 times x is negative 8x. And then negative 8 times negative 3 is positive 24. Now remember, we said that x minus 3 should be a factor. If x minus 3 is a factor, the remainder here should be 0. If we don't get 0 here, we probably either messed up in our division or we messed up in our calculation back up here when we said that f is equal to 3. All right, what does this mean? Well, it means that our function in factored form looks like this: x minus 3 times our quotient here, which is x squared minus 2x minus 8. And now we can factor the quadratic here. Find two numbers that multiply to negative 8 and add to negative 4. Sorry, negative 2. Multiply here and add here. So I'm thinking it's 4 and 2 probably. Negative 4 and positive 2 would add up to negative 2, and we get a product. So our function now is equal to x minus 3 times x minus 4 times x plus 2. There it is, fully factored. And once it's fully factored, it becomes fairly simple to draw a sketch of this. So nice use of the remainder theorem. So the factor theorem really is just a special case of the remainder theorem.